Good morning and welcome back. Today we'll turn to differential forms, and that will be the last chapter of the last section of the chapter on differentiable manifolds. And differential forms are very important in physics because, for instance, the electromagnetic field strength is a differential form, and the question of whether you can find an electromagnetic potential will be a question that will concern us. But in a more general context, differential forms also give rise to something called the deRham cohomology of a smooth manifold. And the big surprise is that although the definition of the so-called deRham cohomology groups employs the differentiable structure of a smooth manifold, it simply tests the underlying topology. So it gives you a tool to construct topological invariants by using the differentiable structure. And of course, that makes it more easily computable than if you would just touch the topology firsthand, and that is why it has such an important role in mathematics. So this is physically and mathematically important. It's 4.7 differential forms and deRham cohomology. So what's a differential form? That's something extremely simple. It's simply a totally antisymmetric tensor. Definition. If we look at the smooth manifold M, then an N form, or often one doesn't say differential, a differential N form is a 0n tensor field omega that is totally antisymmetric. That means if you consider omega, you evaluate it on its n entries, and because it's a 0n tensor field, it eats n vectors, x1 to xn, and the idea is you pick up a minus sign if you exchange any pair of entries, and more formally, that is that if you now consider omega, but you permute the vector fields by some permutation pi, so you look at the entries x pi 1 to x pi n, then you pick up a minus sign depending on whether the signature of your permutation is even or odd. So this is where pi is a permutation of the first n numbers, and obviously x1 to xn, they're all vector fields, so they're smooth sections of the tangent bundle. Any such 0n tensor that has this total antisymmetry property is called an N form. Okay, so examples. I think we saw N forms before because if a smooth manifold M is orientable. Now, what is orientable? Orientable means that you can make a certain pick of charts, so you can restrict an atlas in a certain way, such that the transition functions behave in a certain way. I put this on a problem sheet, and if M is orientable, then there exists a nowhere vanishing top form. I think I introduced this notion before, a top form, and this simply means that, I should say here that we can have 0 less or equal to n less or equal to dim for these n forms, because obviously if I have more vectors in here than the dimension of the manifold is, then any that will always yield 0. So you could have a dim m plus 1 form, but it necessarily would have to be 0 by antisymmetry. And it's also clear that a 1 form is not, the 1 forms are not restricted by the antisymmetry condition. It's void there. And a 0 form neither, but the 0 forms are the 0, 0 tensors are the scalar fields. Okay? Now, but now we have a nowhere vanishing top form, and top form means that the n is the maximal n equals dim m, omega, providing a volume. I think we talked about this before. So that's an example for a differentiable form. And so this provides a volume now in every tangent space because it's a field. B, for instance, the electromagnetic field strength F is a 2 form. That's the Faraday tensor. And finally, C, in classical mechanics, on classical mechanical phase space, let's be more concrete. So if Q is a smooth manifold, that in classical mechanics describes your configurations of the system, then the phase space is T star Q. It's the cotangent bundle where to every point, roughly speaking, you attach all the momenta, all the covectors. So if we're here in classical mechanics in the simplest case. And then on T star Q, there exists even a canonically defined, so you don't need to define this as extra structure, it's already there. On T star Q, there exists a 2 form, omega, which is called the symplectic form. Now, not every 2 form omega is a symplectic form. It needs to have additional properties, but I can't write them down yet. I will only be able to write them down once we develop differential forms a little bit. But one of the ideas, one of the facts is that it's a 2 form. And so you have a 2 form, that means you have 2 entries, you can switch them and you get a minus sign. And that minus sign that you get is the minus sign in the Hamilton equations. You have the Hamilton equations, right? Q dot is dH by dP, and P dot is minus dH by dQ. And this minus, the second minus, in the Hamilton equations comes from here. Okay, very mysterious remarks, very simple. I just want to show you this has immediate implications for physics. Okay, so we introduce some notation. So the set of all n forms be denoted omega n of m. So this is first of all a set, and which naturally becomes is if you equip it with the appropriate structures, you inherit the structures from the sections of the tensor bundle, is a C infinity M module. Obviously it is, because the 0n tensors are a C infinity n module, and this is just a subspace of those, a subspace that's closed under addition, obviously, because the sum of two forms, sum of two n forms is an n form, and the C infinity m multiple of some omega in omega n is again in omega n. That's all quite obvious. And so this is a C infinity m submole. It's obvious. Okay. Now we have this, so that means this is closed under the inherited addition of tensors and the inherited C infinity m S multiplication. But it is not closed under the tensor product. No? However, omega n of m, well, obviously, well, it's not closed, but it's also obviously, okay, I should write, taking tensor products of forms doesn't lead to forms. It's even worse than not being closed, right? Taking tensor products of forms does not yield a form, unless one of the forms was a zero form. Okay, generically it doesn't. But we would like to have a kind of tensor product that again yields a form. And so we define a wedge product, probably saw this before somewhere, a wedge product where that eats an n form and it eats an m form, and it produces an n plus m form, and the important thing is it's antisymmetric again, and we of course need to make sure it is, and we do this as follows. So we take an n form omega, an m form sigma, and we send it to omega wedge sigma. But how is this defined? Well, if this is an n plus m form, we can define it by having it act on n plus m tensor vector fields. Omega wedge sigma acting on x1 to x n plus m many. We can define this as yeah, so we need to take out factors 1 over m factorial, 1 over m factorial, and then we take a sum over all the permutations of the first m plus n numbers. Then we introduce a sign of the permutation, and then we simply take omega omega tensor sigma, we know that guy, and we feed it the x of pi 1 down to the x of pi n plus m. And you know that the tensor product is defined by satisfying the first tensor in the product with as many entries as it needs, and then taking the remaining entries and having them on this second tensor, having them acted upon by the second tensor, and then these two numbers are simply multiplied. So this defines this, and obviously this construction with the sign produces again a form. Okay, and I don't know, the simplest example would probably be you take a one form omega and you take also a one form sigma, and what you then get is omega tensor sigma minus sigma tensor omega. And so the convention I chose here doesn't put a weight here. So there are several conventions you could choose for defining this wedge. You could also put a weight here. Anyway, so this is the convention we're going to choose here. And these guys, of course, just compensate for the fact that the omega and the sigma are already antisymmetric. You don't want to pick up ever more factors here. Okay, so and then quite obviously it goes from here to here, and also importantly, it is of course a bilinear map from here to there. It's C infinity bilinear, because multiplying the omega or the sigma by some function, that will just pull out, and it's additive anyway. Okay, so it's the bilinear, it's a linearity, it's a bilinearity, but because we're dealing with C infinity m modules, this must be a C infinity m bilinearity. There's no doubt about that. Okay, so we have this wedge product, so it's the so-called wedge product, or exterior product. Some people call it the exterior product. Okay. Right. So now one of the questions, well, let's first talk about the pullback. Any questions so far? So you recall that we had, if we have a smooth map H between two smooth manifolds, that this induces maps H star, the so-called pullback maps, at certain points P, but they go the other direction. So they go from T P star n back to T. They go from TH of P star n back to T star TP star m. It's the pullback. Induces pullbacks, right? And obviously, if you free yourself from the idea that this happens at a particular point, but that it happens at all the points, you can, of course, pull back an entire covector field, right? Can be used to define a pullback that no longer speaks about a specific point and that takes a covector field, right? So we can now write a covector field as a one form, because that is what it obviously is. It's a one form. So before we would have written here gamma of T star m, but that's just a one form on n, and it pulls it back to a one form on m. That's just what it does, and it does so by doing at every point this, right? So we only wrote it down for one particular point, but obviously you do this with every point, you then have this map, this pullback map, and that is a linear map. And in this case, it should be, yeah, right. Okay, so we have this, and now the question is, if this works with one forms, does it actually work with n forms? And in fact, it does. So we have the definition. Let omega be an n form. Then we want to define the pullback of that n form instead of a one form. And how do we define this? Well, if it's an n form, so this is supposed to be, this is again on n, because we pull back. We have to start with an n form here, and we can pull it back to an n form here. So the omega is in omega n of n, and now this is, of course, supposed to be, that's what we want to construct, an element of the n forms, but on the original manifold M. Well, okay, how can we define this? We have it act on n vector fields on M. So x1 to xn, and each of those is an element of gamma Tm, that is of the smooth sections of the tangent bundle, or Simply we say these are vector fields. So how do we define this? Well, we define the pullback of a one form by using the push forward on its argument. Now there are several arguments. Well, we use, in every argument, we use the push forward of the vector field, and this is the, as it was previously, the push forward of a vector field, and that's the same construction as we did here. We only defined the push forward from a certain tangent space to the tangent space, to the corresponding tangent space in the image manifold here, target manifold, and now we extend this. We do this at every point, and this is what is meant here. Okay, so this is then the pullback of this one form, and of course you got to check whether it's C infinity linear if you put f's in here, but it is because this one is, and it jumps out of here. And you got to check, if you want to ensure it's a form again, that it remains its anti-symmetry, but obviously it does because we only touch the individual entries here, and the omega is an n form, so this thing is an n form. Okay? It's a very simple extension of the pullback to n forms. And so before we had this statement, vectors are pushed forward and covectors are pulled back. And now we can extend this mantra to forms, any n form. Forms are pulled back. That's it. So, okay. This leads to an extension of the mantra. Forms are pulled back. They're not pushed forward, they're pulled back. Okay, so we have that. Well, and then of course we got the question, how does the so it's okay, so always try to get the perspective. We defined the set of all, or this module of all n forms. Now on this module we established a bilinear. It's not quite true that on this module we defined a bilinear map, because it goes from here to quite a different set. We come to that in a second. But anyway, the question is, how does the pullback distribute over this wedge? That is something that comes up quite often. So we have the, well, theorem. Anyway, it's a result. The pullback distributes over the wedge product. Sounds good. It's very simple. If you got the pullback of a wedge product, and again the understanding is that they can come from very different spaces, so one can come from the n forms and the other one from the m forms. That doesn't matter. The only thing we know is that the total thing here is then an element of n plus m forms, quite obviously. Okay. The pullback of that is simply the wedge of the individual pullbacks. So really the pullback distributes over this wedge. And that can be easily shown, and well, that's just a few lines from the definition. I put this on the problem sheet. So you get some facility in manipulating these expressions. That's quite simple. Okay, so now you see I several times had the urge to say that this wedge acts on a certain space. Well, it doesn't. It takes this n space, the m space, and sends it to the n plus m space. Wouldn't it be so much nicer if there was one space that is closed under the operation of this wedge product? And in fact there is, and it's the so-called Grassmann algebra. So in a sense we want to extend the n-form space the various n-form spaces such as to have the wedge product being a closed operation. So definition. Definition. The C infinity M module G, okay, no, we call it, okay, there are several names being used. We just call it omega of M, so there's no more mention of any particular degree of the form. Well, the degree of the form is simply the n. N is the degree of an n form. You could also call it the rank of the form, because it's, after all, the rank of the tensor. Anyway, there's no particular mention of that, and that guy simply is the direct sum of this module, direct sum this module, omega 1, direct sum this module, plus dot dot dot, plus the finite direct sum up to the dim M forms on M, and we know those are the top forms, there are no further. I remind you that this sign simply means as a set, this is the Cartesian product, but then you equip this Cartesian product with a component-wise addition, and then we immediately write it like this, and that's why I could immediately write here the C infinity M module, because this is a direct sum of modules. And again, the reminder, these are the zero forms. The zero forms are 0, 0 tensors. This is nothing but the familiar functions, smooth functions on M. And these are the one forms, and those are, of course, nothing but the familiar covector fields on M. So we met these guys before. They're kind of special cases of forms, and then it goes on with these higher forms, and here lie the top forms we met. So we have a C infinity M module, and okay, some other name that is being used. I write the triple equal, meaning it's just different notation. Some people also call this the Grassmann algebra over M. Yeah, so this module, but now I already said I call it the Grassmann algebra. Well, what does that mean? Well, I have a module, that means I have a module addition, and I have a module S multiplication, namely with C infinity elements. But in fact, I can also add a bilinear map. So this is a C infinity module, C infinity M module. And we had the definition of an algebra before, that if you have a vector space, and you can extend it to a module, and you equip it with a bilinear map, and the wedge is certainly bilinear acting on here, I write this down in a second, it's of course by C infinity M bilinear. This is called an algebra, right? It's called the Grassmann algebra. On M. It's an algebra of forms. And, well, obviously, where this guy acts on all of omega M, takes two elements of omega M, and sends it to an element of omega M. But we don't know how that works, because we only know how the wedge takes one from here and one from here, say, and sends it to one in here. But that, of course, predestines this wedge here. So it's, in a sense, a new wedge, namely the wedge on the Grassmann algebra. But that says that where this is defined by linear continuation, of the old wedge. And, well, that simply means you take a general element. So, example, you take a general element psi in omega M. Well, not a general one, but you say you take psi equals omega plus sigma. But now this omega is an element of, say, the one forms, and this sigma is an element of the 3 forms, for instance. That could be, right? Now you say, how on earth could you add a 1 form to a 3 form? Well, that's obviously not the addition on tensors of a certain rank, but it is the addition here, because they're all parts of this big space. So this is the addition in omega of m that comes from this direct sum. And so the whole thing is an element of omega of m, right? Looks funny, but that's perfectly fine. And say you have this, and say you have a simple thing like a phi, which happens to be, but doesn't need to be, which is an element of a very specific n-form space. And then you have that phi, and now I need my green color, that the wedge product between the two, because this is obviously a submodule of omega of m, so I can use this wedge that acts on omega of m to wedge these two together. Now the question is, what is this? And this is where linear continuation comes into play. You write it down omega plus sigma, the green wedge, and say the phi. And well, that's fine, because this is in omega of m. This is in the Grassmann algebra. Well, this guy also is in the Grassmann algebra. More particular, it's in this nth subspace. Well, who cares? So this is defined. But now, how is the green one defined? Well, it's defined, and this is the principle or the definition of linear continuation. This is then omega wedge phi plus sigma wedge phi. Now, the omega is from a specific, is a 1 form. The phi is an n form, so this whole thing is an n plus 1 form on m. And over here you have, what is it, a 3 form and an n form is an n plus 3 form on m. And now this plus is the plus on omega m, because obviously you have to take an n plus 1 form and n plus 3 form that can only be a plus as it comes from here, from this omega, but that is of course then defined, and that's the linear continuation of this. Okay, and if you work with this, you say, ah, yeah, well, this is distributive because this is bilinear, but the question is always bilinear where? This is bilinear on omega of m, and you reduce this to the wedge on specific subsets by linear continuation. Okay. There's no secret there. When you calculate, you almost don't see this, but yeah.
Why do you shut them around phi and sine?
Oh, hang on. The omega and the phi and the sigma, well, that was by mistake. I'm sorry. It was by mistake. Okay, so we have this wedge, and this makes the so-called Grassmann algebra. So there is a lot of talk about Grassmann numbers. So I say example, Grassmann numbers, and they're used particularly in supersymmetry. And the usual saying goes, these are numbers that do not commute and that anti-commute. Well, the thing is, it's not the numbers that do not commute. How can it be the objects that don't commute? It can only be an operation that is commutative or not, right? The addition is commutative or not. Well, it is commutative. The Lie bracket is a bilinear map. It can be commutative or not. Well, it's not, because it's antisymmetric and so on. But it can never be the objects that commute or not. It's the operation between the objects. Okay, so that's the first misnomer in this Grassmann numbers, that the numbers do a certain thing or not. It's the algebra that does it. And in fact, the whole secret about Grassmann numbers is, it's not an accident. This is called the Grassmann algebra, you can understand these Grassmann numbers by reducing this to such a Grassmann algebra. Okay, so that is heavily used in supersymmetry and so on, and maybe it's worth emphasizing this at this point. Okay, so there are a few more remarks, but so the question is, what is it about the commutativity or commutation behavior of the wedge theorem? So if you restrict to particular n-form subspaces, so if you take omega to be an n form, and you take sigma to be an m form on a smooth manifold, then you find that omega wedge sigma is, well, you want to compare this to sigma wedge omega. What happens if you flip the two? Well, if they belong to specific subspaces of the Grassmann algebra, then it's very simple to say what they do. They pick up a minus sign, namely how many? Well, the degree of sigma times the degree of omega, minus 1 to the n times m. It's very simple to prove this, but mind you, this is only true, I emphasize again, if the omega is not just an arbitrary element from the Grassmann algebra, which could be a linear superposition of an n form and an n plus 2 form, but if it's a specific n form and sigma is a specific m form, then it's this. And if you have more general elements of a Grassmann algebra, remark, if, what do we call them, psi and phi are elements of the Grassmann algebra, then obviously it's not, you cannot simply say psi wedge phi is something phi wedge psi, because different parts of the psi, which is an n form and n plus 1 form and so on, and of the phi, will have different commutation behavior. So there is no such relation here. Well, I write it's not related, whatever that means. If you're coming from the full Grassmann algebra, then you have to break it up to its individual summons with respect to this direct sum, and in each of these summons, so to speak, well, can be different. Anyway, everything is said. There you can apply this rule. Okay, that's important. So there's no overall commutation or anti-commutation of the wedge if it acts on, so we had it in green before, if it acts on general elements of the algebra, then you need to break it down by linear continuation and do it on the individual factors. Okay, this just as a warning. Okay. So we have this, don't commute nor anti-commute. Right. Aha. Yeah, and now the question is, what about differentiation? So we had differentiation of functions in terms of the gradient, and we had differentiation of maps in terms of the push forward. After all, right? That was the differential of the map. The question is, what is the differential? What's the derivative of the forms? And so we first recall that we had this gradient at a point. So if we had a smooth function f, we could define this gradient operator, but now not at a particular point, but we can define it on any function, and what it yields is a 1 form. Because what we had before, okay, so I write it down, so f is sent to df, and that's a 1 form. Well, why is that? Because I can define this 1 form at a point. Well, if it's a 1 form, then at the point it makes it an element of the cotangent space, right? And I can define this by what I wrote down before as d sub pf, and this guy was defined, right? D sub p we defined. Now we do this at every point, and of course we get this extension of the dp to a d that takes a function to a covector field, okay? But now we want to extend this, and we want to extend this to to a covector field, and this guy here is of course the 0 forms. So you have here, aha, so this D we already have takes 0 forms to 1 forms. And now what we would like to do, we would like to extend the D such that it takes an n form to an n plus 1 form. So this can be extended to n forms. Now, you ask, okay, you extend it to n forms, why don't you extend it to any tensors? N forms are just specific tensors, and the answer is, on tensors, you cannot write down a derivative without adding further structure to the manifold. So the differentiable structure we have on the manifold is not enough to define a so-called covariant derivative on arbitrary tensors. But on forms, on these totally anti-symmetric tensors, there is a notion of derivative, so-called exterior derivative we're going to define, that can be defined just in terms of the differentiable structure. So in accordance with our philosophy that we always want to keep track which structure, which operation, which definition we can have at what structural level in our building, this is an important point. Okay, so this can be extended to n forms, and we have the definition. The exterior derivative operator, D takes an n form on M and sends it to an M form over M, and it does so by virtue of the following definition, where d omega, okay, so omega is an n form, so this whole thing is an n plus 1 form once I'm finished, so I can define it by having it act on n plus 1 covector fields, right? So these guys here, they're, no, vector fields, I'm sorry. There are smooth vector fields. If I know the action of an n plus 1, I'm sorry, this is not m, this is n plus 1. I raise the degree of the form by 1. If I have this n plus 1 form act on n plus 1 vector fields, and I know how that works, then it's defined. So how is this defined? I take the sum from 1 to n plus 1, so as many as I have entries here, and I apply the ith entry, the ith vector. What can I apply a vector to? I can apply a vector to a function. How do I get a function? Well, I take the original omega, which is just an n form, and I feed it with all the vectors I fed the n plus 1 form here with. Well, that's of course not possible, because that's 1 too many. Well, the ith one I let act on it, so I cross out the ith one. That leaves you n in here, and I act with the, that gives you then a function, because this is a function, because this is an n tensor. It eats n vector fields. It's a function, and I act with this vector on the function. That's kind of the directional derivative, and I do this democratically for every entry. So I sum over all of these, but I want this thing to be a form again, so it needs to be anti-symmetric, and in order to ensure this, I have to put a minus sign occasionally, and I put a minus sign with the power I plus 1. Yeah, that's what I want, precisely. That's what I want. That's not all of it. Then there is a plus. And now there is a term that goes over pairs. Here I took individual every one, but now I take all the pairs, well, but all the ordered pairs. So I take I less than j, but both of them, well, run from 1 to n plus 1. And here I have the original omega, which can eat n vector fields, but the first entry I fill with the so-called commutator of two vector fields. I'll define that in a second. And then the remaining ones, x1, 2, then there is the ith one, then there is the jth one, and then there's the n plus 1th. Well, I already used 2 of those and made 1 of them, so I cross out the ith, I cross out the jth, I keep the others, I took 2 out, I put 1 in, that means I have n fields, I feed this guy, and the anti-symmetry is already taken care of by this commutator, and that is the definition of this exterior derivative. It's the coordinate-free definition, and all right. So, well, proof. You ask why proof? It's a definition, isn't it? Well, we have to make sure that this d omega is indeed an n plus 1 form. Okay, how do you do this? Well, d omega antisymmetric, totally antisymmetric, that is clear from the definition. You check that, you exchange any 2, you pick up an overall minus sign. But that's not the only thing we need to check. We need to check that it's C infinity M multilinear. So that in each of the slots it's additive. Well, that's quick. That in each of the x's it's additive. That follows immediately. Oh, I have to still define the commutator, I'm sorry. But what you have to do is, the crucial thing always is it, if you put a function, if you multiply any of the entries by a C infinity function, does this guy pull out? And in fact, intuitively, one wants to have this, but this extra term here is to ensure the C infinity multilinearity so that this is really a tensor field. Okay? So, yeah. So I need to explain to you what this commutator is. Well, the commutator of 2 vector fields okay, so what is this? So let's make an aside of this. Aside, commutator of 2 vector fields. An extremely important notion also later on when we discuss Lie groups in the algebras. Commutator of 2 vector fields is the following. You take x and y vector fields on a smooth manifold, and if you consider x acting on the result of yf for any smooth function f, okay? And then you subtract y acting on x on f. Well, this expression is defined, you know this expression, and it gets a name x comma y on f. And what you can show, and that's the problem sheet, show problem sheet, that only this combination x comma y, but not x after y or y after x, but only this combination is again a vector field. Okay, so you can take 2 vector fields and you make a new vector field, you construct a new vector field by taking this so-called commutator. And it acts on a function and it has the C infinity multilinearity property, it's a vector field. Okay, and so this commutator we use here. Okay, that's this. And it's of course antisymmetric. The commutator of x, y is minus the vector field commutator yx. Okay, so let's have an example. I think one should have seen this once, or I should demonstrate it once. Let's consider the case n equals 1. So we take a 1 form and we calculate the exterior derivative. Okay, so n equals 1. That means we look at d omega, and that is then a 2 form. So I write vectors x and y instead of x1 and x2. Okay, so if omega is a 1 form, then d omega is a 2 form, so we should be able to write down this number or this function here. So according to the definition, what do I have to do? I take the first one, then the second one. So I take the x and let it act on the omega as it acts on y, minus I take the y and let it act on omega as it acts on x. And x is the first entry, and so it's 1 plus 1 is 2. The sign goes, here the sign stays. That's already this entire sum. And then over here, no, I forgot something. Here, I need minus 1 to the I plus j. I'm sorry. So there's also a sign here, and it takes the I plus j. So I claimed before that antisymmetry is taken care of by the commutator. That's not true. You need this additional sign. And now, so you have to go over all pairs. Well, the ordered pairs, there's only one ordered pair. There's only the ordered pair 1, 2 you can go over. But then you pick up a minus sign here, because minus 1 to the 1 plus 2 is minus 1 to the 3. So that's the minus sign, and you just have omega of the commutator, and there are no further vector fields. So that is it. Now, let's check for this particular example. Let's check C infinity multilinearity. Well, additivity is obvious, so check C infinity M scaling. And because it's anti-symmetric by construction, it suffices to check the scaling in one entry, because then in the other entry it's obviously also there. So let's try to fit this into this line. So we consider d omega of x comma fy. So I scale the y, and what I want to show is that for any f in C infinity M, the f pulls in front. That's important. And we'll see that we need the second term here, so this last term in this expansion, to achieve that. So how does it look like? Okay, so we plug in here. The y is scaled. So this is x of omega fy, but there the f immediately jumps in front. It's f omega y. Why? Well, because the omega is a co-vector field. It's, of course, C infinity linear. Minus. Well, here the f already is right in front. F times y omega of x. Okay. Now here we need to work a little. It's omega, and now it's the commutator of x and y. And there is an f in here in between. So how does that look like? Well, that's an x acting on fy minus fy acting on x. This finishes like this. So we go up here, equals. Aha. So now the x is a vector field. It acts on this product of functions, but because it's a derivation, it acts by the product rule, by the Leibniz rule. So this is xf times omega of y. And there's a second term, namely it acts on the second factor, plus f x on y, x on omega on y. X on omega on y. This is just the first term here, because x as a vector field is a derivation. Then comes minus, well, this term we do not massage any further. This is fy acting on omega of x, all right. Now this last term we have to work a little. Omega is a one form, so it's certainly additive, so we can pull this apart. So we get minus omega of the first summand, but let's work on this first sum. That's the same thing. That's the Leibniz rule, xf, and then y, plus f, and then x on y. Okay, that's the first term, close bracket. Well, I do not quite close the bracket yet. I do not use that yet. I continue minus f, y, x. Aha, but now the whole thing transpires here. I now see that I rather use the additivity at this point, and I take this together. Well, let me discuss it like this. So I just take the second term here, including the minus sign in front, only the second term. This is minus xf, because xf is only a function that jumps in front of the omega, because this is a covector field, xf omega of y. And then the remainder here is minus omega fxy minus fyx, but the f jumps in front, so I can put the f here, omega of x and y. Aha, so that was just the second term, but now xf omega y minus xf of omega y, this goes against this, and this term, and that term together is simply f times d omega of xy. So in fact, the f pulled out. And hadn't it been for the second term here, so the last term in here, it would not be C infinity linear. It would be R linear, but not C infinity linear. So for this to be a tensor field, we need the second term. Okay. All of this without choosing any components, any bases, because we don't even know whether we have a global basis. So we do it this way. Okay, so that was this. And so then there are two more remarks. So the question is, how does this D commute, how does it talk to the wedge? So let omega be in n form, and let phi be in m form, then the D of omega wedge phi is, now this is a product, it's a kind of a product, it's an antisymmetric product, and here I have some kind of differentiation. So we expect something like a Leibniz rule. That should be a product rule of some sort, but it's not an exact Leibniz rule, because neither is this an ordinary differentiation, it's an exterior differentiation, nor is this an ordinary product, it's an antisymmetrized product. And in fact, what it is, you act on the first one, all right, so that's d omega, and then afterwards you take the wedge. Well, if you want, you can put brackets around here. And if it was an ordinary Leibniz rule, you'd put a plus, and then you'll keep the first one, and you apply the derivative operator to the second part, and that would be the Leibniz rule. But it simply isn't like this. There is an extra sign factor here, but only the degree of the omega counts. So this degree here is irrelevant for the formula here. Okay, so this is this is kind of a graded action. One calls this a graded action, and up here you call this a graded algebra, because it depends on the degree of whether this commutes or anti-commutes. Okay, so we have this thing. That's the first theorem. That can be proven. Maybe I'll torture you with it on the problem sheet or not. Anyway, this is to be memorized. And the other really wildly important theorem, so it deserves a box or something, because it comes as a gift, it comes in a box, is that the pullback commutes with the exterior differentiation. So exterior differentiation commutes. Well, I put this in quotation marks, commutes with the pullback. How does that look like? Well, so you take the pullback of some exterior derivative. And it's in fact true that that is the exterior derivative of the pullback. Right? Okay. So, well, obviously, if this is an n form, then this is an n plus 1 form. So this is the pullback of an n plus 1 form, whereas this is the pullback of an n form, and it only becomes an n plus 1 form afterwards. So in a sense, these are different d's. So this d here, takes an n form, say, takes an n form and makes it to an n plus 1 form. That's what we did all the time, right? And this d here, well, it's the same d, but it's the d acting on a no, they're both, no, it's both the same. This is an n form, and this is also an n form. I'm sorry, so they're really the same d's. I'm sorry. Agree? Yeah. Pardon me? On a different manifold. Oh, well, that is true. Okay, so yeah, okay, that's true, but that was not the point I wanted to make. They're certainly on different manifolds. So that's the one. So if it's the pullback, that must be the one on the manifold. So if H, I should say H is a smooth map from M to N, then this omega must be a form on N, and this omega must be a form on N. And exactly, so this D acts on an N form on N. So acts on an n form on n to make it an n plus 1 form on n. That is right. And here, this d, because the pullback has already happened, takes, all right, an n form, but on m, and makes it to an n plus 1 form on m. So in a sense, they're not the same d's, but and so in that sense, you should say commutes, because not the same operator, but symbolically it commutes. So you can remember it that way if you know there what you are doing. And of course, similarly, the action of D extends bilinear continuation, or at least additivity, to the entire Grassmann algebra, right? So you can actually take an element of the Grassmann algebra and map it to an element of the Grassmann algebra. It just so happens that this element was a sum of a 2 form and a 3 form, then the result will be a 3 form and a 4 form, okay, in the 4 form subspace. But this is also closed here. Okay. So there's this extension. So let me give you 2 physical examples. And they're very brief because, in fact, we don't have enough technology yet to embellish them. But the first example is a well-known one, and that's Maxwell electrodynamics. But actually, I shouldn't say Maxwell electrodynamics. I should say any electrodynamics. Okay? So, I mean, what is Maxwell electrodynamics? If you go to the books like Jackson, they say Maxwell electrodynamics is the Maxwell equations. They give you 4 equations and that's it. Well, the question is, are there other electrodynamics? And if there are, which of the equations can you change without leaving the domain of electrodynamics? And, well, any electrodynamics has to talk about the field strength, F, and in fact, dF equals 0, so F is a 2 form. We had this before, the electromagnetic field strength. If you think of it in components on a 4 manifold, you have the E and the B field in there. Okay, you saw all of this before, I hope. Otherwise, I'll torture you with it on the problem sheet. Well, I'll certainly torture you with it on the problem sheet. But then the dF is a 3 form, and you require that this 3 form, so there's the 0 on omega 3 of m, require that this 3 form be 0. And this has a name. This is called the homogeneous Maxwell equations. So it looks like only one tensorial equation instead of the two Maxwell equations, but in fact it covers both. Okay? Now, what do you usually do with these homogeneous Maxwell equations if you have them in the standard formulation? Well, you look at them and you put your rods on your curls and your divergences, and you play all these games, and you find in standard electrodynamics or standard theory, as it's taught in classes, you find that this 2 form can actually be expressed as the exterior derivative of a 1 form. Okay? So f is a 2 form, and now this can be written as this exterior derivative, and then this guy, if this guy is called the field strength, this guy is called the gauge potential, or simply the potential. Okay? Now, what I would like to draw your attention to is this implication arrow. Is it really true that from the vanishing of the exterior derivative of f, you can conclude that there is an A such that the f is a dA? And the answer is yes, that's certainly true, if the space-time on which you work as a smooth manifold is R4 as the smooth manifold. Okay? But it fails to be true as soon as you start taking out entire lines and stuff like this from R4, then it starts failing to be true. Okay? That's one thing we're going to investigate, and the last part of today's lecture will also have to do with that. That's the first example where the exterior derivative appears in physics. The second example is on symplectic manifolds. So we're going back to our classical mechanics example. And there I already said that you have something like, well, it's just a name, you call it a symplectic form. And I already told you that one of the requirements on a symplectic form is that it be a 2 form. And that's only one of the conditions. There's another condition that says it needs to be non-degenerate. Let's forget about this at the moment. We'll come to that, back to that later. But you also require that this 2 form, again, is very similar to here. It's essentially the same thing. It's only this is always on R4, whereas this can be on any cotangent bundle. Oh, I'm sorry. So the omega, I'm terribly sorry. The omega doesn't live on M. It lives on the cotangent bundle of some configuration manifold. You can generalize this to a symplectic manifold M, but we're not there yet. So it's a form on the cotangent space, on the phase space, and we require this form be closed. Well, it turns out if you're here on the cotangent bundle, this is always true because on T star Q, you can always write down a theta, and this theta has the form pi dqi. What are pi and dqi? Well, pi and dqi are the components of a point in the cotangent bundle. So this goes to dim q, and then p1 to p dim q, and very much like we so these are coordinates, right? Very much like we construct a coordinate system on the tangent bundle, you can construct one on the cotangent bundle. You can write down this guy, and then indeed it follows that if you define omega as the exterior derivative of this symplectic potential, you see this is really an analogy, symplectic potential, then indeed you find that d omega is d theta, and you calculate this and you get 0. Aha, so if your phase space is the cotangent space of some configuration space, then this is trivial, that the d omega is 0 if you define the, well, you can trivially find one such thing, at least in some local patch. But in fact, you can always. But then you could say, well, let's not have the cotangent bundle of something. Let's just have an even dimensional manifold M here and equip it with such a 2 form omega. And then you have to require by force that the d omega is 0. And then you call this whole thing, if this omega also satisfies some non-degeneracy condition, you call this a symplectic form, and you call the pair M and omega a symplectic manifold, and that's essentially the whole business of Hamiltonian mechanics, and we'll come to that. Okay. We'll come to the fact that if you come from a Lagrangian formalism, you go to the cotangent bundle, but as soon as you start doing canonical transformations, you violate the bundle structure here, and so you need to think more generically in terms of a symplectic manifold. Anyway, if these remarks seem mysterious to you, just take them as examples where in electrodynamics and in classical mechanics, the exterior derivative plays an important structural role. And the question under which circumstances the vanishing of an exterior derivative implies that the form on which it acted itself can be expressed as an exterior derivative is a very important one, and it gives rise to the so-called cohomology theory, which I'm now going to discuss. Okay, so deRham cohomology. Okay, so the basic theorem on which this whole business of cohomology is built is the following. D squared equals 0, full stop. Well, proof. Well, obviously by D squared, we mean that you apply D and then you apply D again. So it's D circ D. And so it can act on some function, or it can act on some n form. So let's say omega is some n form for definiteness. So this is the d of the form. So clearly this is an n plus 2 form, the result. But in fact, the claim is that it's already 0. And well, you can show this directly from the definition of the d. There was a little involved. You can show it immediately in local coordinates. Because in local coordinates, the d omega of an n form can always be expanded, and that you should do in detail on the problem sheet in order to get the factors right. But in fact, there are no particular factors. It gets expanded in the form omega. It's an n form, so it has indices a1 to an with respect to some smooth basis. For instance, the coordinate-induced, well, we're using coordinates here, coordinate-induced basis. And then you take the derivative, so I should not use that notation. I should use the partial derivative notation, dB, del B, on these functions. Because if omega is a n form, it's a field, right? It's a tensor field, so it has components that are functions, okay? And so you take the b partial derivative of the component function omega a1 to an, and then, of course, you have to get back an n plus 1 form, and that's indeed xb. We know this is a 1 form and a 1 form field. Wedge, so you can wedge these fields, wedge dxa1, wedge dot dot dot, wedge dxan. So you can always, in local coordinates, expand the exterior derivative like this. But then it's immediate that the d of omega must then be the del c del b of omega a1 to an. And you have dxc wedge dxd wedge dx a1 wedge dot dot wedge dxan, and that looks all right. However, these wedges, these are all 1 forms, so the exchange of any 2 of them picks up a minus sign. And you have all of these indices contracted here, the b and the a1 to an, with all these indices down here. Now, if you have such a situation, then it actually turns out that this is the same as, and I write it down only once, omega a1 to omega an dxb. So I copy the expression dxa1 wedge dxan. It's the same of whether I put antisymmetrization brackets here or not. Now, do you all know these antisymmetrization brackets, or you want me to explain them? Explain, okay. So what are those? Well, the idea is if you have an object, okay, an object O, that carries indices m1 to mf, okay, then you want to define an antisymmetrization bracket as follows. It's the sum over all permutations pi of the f numbers here. And you write here the sign of the permutation. And then you take this object O and you look at pi of m1 down to pi of mf. m1 to mf. You pick up the sign and you also, that's my convention here, and you also introduce a factor 1 over f factorial. That's the definition of the antisymmetrization bracket. And there's also a symmetrization bracket. That's then round brackets around indices. It's exactly the same thing, but without the sign of the permutation. It symmetrizes and doesn't antisymmetrize. That's one thing you need to know about this. Okay, so that's the brackets. That's just notation, okay? Notation. But there's also a little result to be learned. So assume you have an object with two indices, A, B, and you have another object with two indices, A, B. And I really say object. It doesn't mean what it is. It doesn't mean that these are scalar coefficients and this is a two form which is labeled by A and B like it is here. It is a fact that if this one is already anti-symmetric, so then I can put these brackets there because the result is an anti-symmetric thing. That is the same as writing the indices down here. Okay, and this can be easily proven. So one says that if you fully contract a number of indices, this could be symmetric, anti-symmetric, whatever, you contract them with something totally anti-symmetric, this induces an anti-symmetry down here. I mean, it's a two-liner. Try to show this from the definition. It also is true for more indices. And that's the case here. Back here, this is manifestly under exchange of any of the dx somethings with another dx something else. You pick up a minus sign. So all these indices up here are totally anti-symmetric. That induces an anti-symmetry down here. Okay? So whether these had been symmetric or not before, in this combination they are. And there's really an equal sign. Okay? So if you don't see this immediately, calculate it at home. It's very important to be able to see this because it simplifies many calculations like this one, because I see, so up there, now this whole sequence of indices C, B, A1, A2 to AN, all of these are already anti-symmetric by definition of the wedge product. So there is no harm in me putting the antisymmetry brackets there because any repeated factors are killed by the F factorial. But that also means it induces an antisymmetry on all of these, C, B, A1, to AN. But then there's the next result, that is if you have something that is symmetric and you have something that's antisymmetric in indices and you contract over these, you necessarily get zero. And that's exactly what happens here. These two are of course already symmetric if this is at least, if these coefficients are at least C2, according to which lemma or theorem? Schwarz, that's right. Schwarz theorem tells you that this is 0. Aha, there you go. So at least in a coordinate chart, we showed this, that whatever form you act upon, if you act upon it with D twice, you get 0. So this 0 is the 0 on the n form space, on the n plus 2 form space, if the D originally here acted on an n form, right? So D squared is 0, and that's an essential thing. Now, why is this so important? You say, okay, that's an amusing fact, let's push on. But in fact, lots follow from that. Okay. This implies that we have a sequence of maps. So now let's be careful. So I start out, well, almost, I start out with the 0 forms, that is the smooth functions. But actually, I will have one more space in front of that. Now, if I have a smooth function, so forget this arrow at the moment, I can apply the D, and I get a 1 form, right? I increase the degree by 1. Once I have a 1 form, I can, of course, use again the D and produce a 2 form. And so on it goes, dot, dot, dot. I go by D, D, D. I finally reach the n forms. From there, I go to the n plus 1 forms by the D. And so it continues until I reach which forms? Until I reach the top forms, namely the forms of rank dimension m. And once I reach them, and I again act with D, we know we get a dim m plus 1 form, but that's always 0. So we write 0 here. Yeah, it's a kind of a vector space with bracket 0, but let's write it like this. It's customary. And the same here. I start from a trivial vector space that has only one element. So probably, to be very precise, one should write the vector space that just consists of one element. There are no smaller ones. And I can extend the definition of my D by defining this green D here, okay? And the green D takes you from 0 to, well, where should it take you? It takes you always to the 0 in here. So the green D just takes the 0 in here to the 0 in here. So this is defined to be the 0 in C infinity M in the 0 forms. Okay, so I extend this a little to have this entire line, and so it's also customary to not write these brackets. So it's the vector space of consisting just one element. So I have this sequence. Well, I had the sequence anyway. That's nothing new. But what does the D squared equals 0 tell us? Well, it tells us the following. It tells us that, well, let's first make two definitions or recall the following definitions from linear algebra. So if we have a map phi that takes us from one module P to another module Q. So P, Q, let's say there are C infinity M modules. Okay, specifically, but quite independent of the C infinity M. If you have a linear map between two modules, you probably saw this between vector spaces, but then you can define two things. You can define something called the image of the map, which is a subset, of course, of the target of the map, and it is all those objects phi of P for P in P. It's all the images. And you can define a subset of the domain called the kernel of phi. It's called the kernel of phi. That's just a short name for all those p in P for which phi that are sent to 0 by phi. Now, the kernel is even a subvector space, a submodule of this phi here, okay? And if you now look at the particular case for D, right? So all these D's are actually different D's, and let's focus for a moment, because they come from different spaces. They always are called D, but obviously this map here, from the nth to the n plus first, is a different map from the one that takes you from omega 0 to omega 1. But we call it D. Okay, you have to keep in mind from where to where the D maps. So I could ask about this green D, what is its kernel and what is its image? Okay, so I can certainly look at the kernel of the green D, and that will be a subset of omega n. And I can look at the image, but now let me do something different. I look at the image of the D that was once before. So the red D here. So I should have rather looked at this. Okay. So the image of the red D, that's this other map, left and right of this. This is also a subset of omega n, right? So this kernel of the green D and the image of the red D, they lie in the same form space. Is that right, clear? That's clear, no? Okay. And so what does it now, in this language, what does it mean that we have D after D equals 0? What does this translate to? Well, the first D takes you here, the second D takes you to 0. That means the image lies in the kernel, right? So that means that the image of the red D is a subset of the kernel of the green D. Okay? Well, it's a subset. Now the question is, well, it's a subset. And let's give elements in these subsets names, because they're very important subsets. Well, it's just terminology. So we look at omega n minus 1 of m. We go to omega of m, omega n of m. We go to omega n plus 1 of m. So we look at these three spaces as parts of this, as a part of this sequence. And we have the red D here and the green D here. Okay? Now we want to classify, subclassify forms in this space. So we call an omega in omega n of m, right, in this blue space here. We call an n form called exact. It's called exact if this omega lies in the image of the red one. And we call an omega, well, and it's called the same omega, not the same, an omega in the n forms is called closed if it lies in the kernel, well, not of the same D, but of the next D. Okay, so in general, form will be neither exact nor closed, but those that lie in the image are called the exact forms, and those that lie in the kernel are called the closed forms. Well, it's immediate that d squared equals 0 implies, or rather here, imd in the kernel means every exact form is closed. Okay? Because you can think of the exact forms as follows. You can say for an exact form, omega exact, for practical purposes, well, it's just true, is there exists a form alpha of 1 degree less, of course, such that omega is d alpha. That's exact. And of course, closed, omega closed, is that d of omega is 0. So this is just a reformulation, and you need to be able to switch between this formulation of exact, which is of course precisely this definition, but here it's useful to think in terms of images and kernels if you think about the sequence. Okay, and now we go back to this electrodynamics problem. So example, if you have a one form A, if you have an electromagnetic potential, and from it you define the field strength as its exterior derivative, then of course it follows that the d of the field strength, being the d squared of the A, is 0. So all right, if you have such a gauge potential, you satisfy the homogeneous Maxwell equations, and that's of course the reason why we choose that in electrodynamics, if we can. But the question is whether you can actually take this implication arrow and turn it around. Can you already conclude from the homogeneous Maxwell equation that there is an A such that F is exact? So that means the Maxwell, homogeneous Maxwell equations, homogeneous Maxwell, what they say is that the field strength is closed. In this language, that's what the Maxwell equations say. Now, you may ask, well, if that is so, is this closed one also exact? Right? Because that's just, the image is just a subset of the kernel, but is it equal to the kernel? That's the question. Okay? So under what circumstances are these inclusions at every point of the sequence actually not inclusions but equalities? That's a question you can ask. That's a question of immediate importance, for instance, in electrodynamics and of course in many other fields. So in an attempt to make the subject incomprehensible, people further rename, so further needless terminology. Not enough that we recognize that the image of the D is important and the kernel of the D. I now no longer emphasize the different Ds. You should always go back to this, right? They actually call the image is the exact ones. They call them Bn. If this is the image of the D that results in an n form, this set, and if you look at the D whose kernel is a space of the n forms, then you call these exact forms, you call them, the closed forms, you call them Zn. So these are the exact forms, the space of exact forms, and this is the space of closed forms. So you again rename a clear object. Well, maybe there's some virtue to it because you say the exact ones of degree n, the closed ones of degree n, and otherwise you here have always to say this is the d that acts on the omega n minus 1, and this is the d that acts on the omega n. So here this, well, okay. But anyway, that's the traditional notation, okay? And so again, we know that the image lies in the kernel, so we know that the exact ones lie in the closed ones, okay? And the question is, when are they equal? Okay, question, are they equal? The answer is no, okay? But there is the Poincaré lemma, and the Poincaré lemma says that Bn is actually Zn for all n greater than 0, and n equals 0 we look at in a second, if m is some Rm. So equality holds on Rm. So on some Rm, apart from the case n equals 0, all the forms are actually, all the closed forms are exact, and all the exact forms are closed. It's the same thing. And therefore, in electrodynamics on R4, if you just have an infinitely extended space-time, you can go back and forth between the homogeneous Maxwell equations and the gauge potential. That is just equivalent. But that is just on R4. And already if you take out of space, say you pose some longish electromagnet somewhere, right? Some coil, then you already start disturbing this business, right? And that plays, for instance, a role in the, what's it called? The effect in quantum mechanics, the Aharonov-Bohm effect and stuff like this. So it's not very esoteric to kind of say you're not on R4. You can easily bring up experimental setups that produce this effect. Okay, are they equal? No, but on R4. But that's not the whole, that's of course just a very special case. And what if not? That's the next question. So question 1, are they? Question 2, what if not? Well, what if not? Then we would like to quantify by how much the closed forms fail to be exact. By how much do closed forms fail to be exact? It's one thing to know it's not the same. The other question is, how different is it? And if we want to quantify, and we have one subspace in the other, we can have the following definition. The nth deRham cohomology group nth deRham cohomology group is the quotient vector space with the nice name H, like homology. So it's the H in the homology. If we were defining a homology group, we would put an index down here, but because we're defining a cohomology group, we put an index up there, Hn of the manifold, okay? And it's defined as the closed forms n, Zn, quotient with the exact forms, with the exact n forms. And now you might ask, what is this quotient of vector spaces? Well, this is just short notation for saying you have on Zn, you have an equivalence relation that relates to forms omega and sigma that are already closed, that relates them by definition if and only if their difference is actually exact, right? So this twiddle has to do with the exactness, okay? And therefore, this guy here, what we write Zn by Bn, is just another notation for Zn modulo twiddle, but this twiddle depends on the exact forms, so it's modulo twiddle Bn, and then people forget about the twiddle and just write Bn. Okay, so that's not something new, it's just the old game of equivalence relations and looking at the equivalence, the set of equivalence classes that is at this quotient vector space. Now, in order to, okay, so we have this. Now comes a theorem. Before I give you the first example of this, I quote a theorem, and that's deRham's theorem. And I don't quote it in its technical detail, but only in its philosophical, well, in its conceptual implication. The deRham's theorem says that the Hn of m only depend on the topology of m. Now this is of course remarkable because everything in here, so it's supposed to be an exclamation mark, because everything in here is defined by exterior derivatives, how they relate to each other, and exterior derivatives have everything to do with the local differentiable structure, if you wish. So I can put an unneeded word here, but I write down there, it depends on the global topology. So for instance, how many connected components your space has will show up in the H0 here. Okay, if you put n equals 0, in fact, well, maybe we can still quickly do this. That gives Hn of m. So okay, I just write as a remark or example. I'll put this on the problem sheet due to time reasons. The H0 of some smooth manifold, real manifold, is actually isomorphic to R to the number of connected pieces of M. Okay? It's the number of connected pieces of M. And that's very easy to prove if you think about what the covariant, what the exterior derivative does. If you see that the closed forms, a form is closed if it's, so the zero form is closed if its exterior derivative vanishes. But the exterior derivative of a zero form is the exterior derivative of a function, is the gradient of a function. Okay? If the gradient of a function vanishes everywhere, that means it's a constant function. But if you have a space consisting of several pieces, this piece and another disconnected piece here, the function could be constant on this piece with one value and constant with another value over there. If you do this, and then you also ask yourself what are the exact forms, exact zero forms, you come to this result. I put it on the problem sheet. Okay. If you want to calculate higher cohomology groups, which is very interesting, the practical calculation, even in the simplest cases like for R, so first of all, from here it follows immediately that H0 of the real line is the same as H0 of the circle. This is all R because this is connected and this is connected, has only one connected piece. But then there's other stuff like Hn for n greater or equal to 1 of the real line, they're all the vector space with just the element 0. Okay? So you can show this, but in order to show this, you already need integration on manifolds. Not in a heavy way, but you need it, and we're only going to do this later. But I wanted to give you the theorem first, so the practical calculation is one thing, but the fact is another one. Again, from d squared equals 0, the central underlying identity there, we get this sequence with inclusions where always the images are included in the kernels of the next map. And then if we want to quantify how much the images deviate from the kernel or do not give the entire kernel, we can quantify by modding out the exact forms from the closed forms, and that gives you the deRham cohomology groups. And although everything depends on the differentiable structure, the objects you get, the groups you get, you remember we had the fundamental group was also a group concerned with the topology. These are also groups concerned with the topology. They're built another way. They have a certain relation to the fundamental group, but it's not so simple, these cohomology groups. But anyway, we learn purely topological information, the topological invariance. Right? So two different differentiable manifolds that are built on the same topological manifold will have the same deRham cohomology groups. And you know how difficult it is to actually really deal with the topology, to really use the open sets to construct objects. It's much easier to calculate stuff like this, and so you get this. And now again, the Poincare lemma was that just this essentially is the Poincare lemma for the real line, but it also extends to Rm. All the n greater equal to 1 deRham cohomology groups are just the 0 vector space. Of course, the 0th isn't. The 0th is just R because it's one connected piece. So that's the basis of cohomology theory, and it of course carries significance. You can also show that the other identity that I wrote down. Okay. So let's continue next time. Okay, thank you.